Okay, so for today's real-life Orgo, Group 25 is going to explore the topic of chemiluminescence. Have you ever wondered how fireflies glow? They do so through a chemical reaction. When chemical reactions take place, energy can either be absorbed or released. One way it can be released is through the emission of light. This is the definition of a chemiluminescence reaction. In this video, we will explore this process with examples in nature and in human practice. The basic chemistry behind the process of chemiluminescence involves oxidation of a molecule leading to an excited electronic structure. As the molecule returns to its ground state, photons are emitted, making it glow. Additionally, in chemiluminescence, the light produced is cool, as less than 20% of the energy generated is in the form of heat. This means that the majority of the energy released is in the form of light, responsible for the glow we see from fireflies. Pictured is the proposed mechanism for luminol, a synthesized molecule that we will discuss later in the video.
Fireflies are one of the most common organisms that use chemiluminescence. The main reason they use chemiluminescence is for communicating with other fireflies, mating, and fending off prey. All fireflies have the same luciferase enzyme, which is the key reactant in their chemiluminescence reaction. However, fireflies differ in their pH, causing different colors to emit. For example, when the keto version of the emitter is formed, the pH in the firefly is around 6, which causes red light to be emitted. In contrast, when the enolate dianion is produced, the pH in the firefly is around 8, which causes the familiar yellowish green light to be emitted. As we will discuss later, fireflies are not the only organism to use chemiluminescence. The chemiluminescence reaction in fireflies is different than what we saw with luminol. With fireflies, the reaction can be described as the luciferin being oxidized to form an excited oxyluciferin state with the assistance of a luciferase enzyme. Pictured is the proposed mechanism for this reaction. The mechanism begins with the formation of a luciferase enzyme that all fireflies have. After the enzyme has been formed, deprotonation occurs due to the amino acid residue from the luciferin. Next, the oxidation of the anion forms the electronically excited oxyluciferin state and carbon dioxide. As stated before, there are two different products that can form, the keto and the enolate.
In addition to fireflies, a variety of other organisms utilize a similar enzyme pathway, including certain species of beetles and jellyfish. Another example is the sea pansy. In the sea pansy, luciferase interacts with the green fluorescent protein, which has other important biological applications, to produce a glow when irritated. Dinoflagellates, a small eukaryotic organism, also produces a small glow when disturbed. This creates a magnificent effect in large colonies of these organisms. For example, the mosquito bioluminescent bay in Puerto Rico is a popular tourist destination because it contains up to 160,000 microscopic dinoflagellates per liter of water. This leads to a spectacular light show if you decide to go swimming or kayaking through the bay, as demonstrated in the bottom left picture.
Do you see anything?
I see a light.
A light?
Yeah, over there. Hey, Conscience, am I dead?
No, I see it too. What is it?
It's so pretty.
I'm feeling happy, which is a big deal for me.
I want to touch it.
Ooh. Hey, come back. Come on back here.
I'm gonna get you.
I'm gonna get you.
I'm gonna get you.
I'm gonna swim with you.
I'm gonna get you.
I'm gonna be your best friend. Good feelings gone.
Bioluminescence has a variety of useful applications in nature. It is used by living things to hunt prey, escape predators, and find mates. Some fish, most notably the anglerfish, use bioluminescence to attract curious prey. Others use luminescence to escape predators. For example, some species of squid that lack ink sacs flash to startle predators. With a startled predator caught off guard, the squid tries to quickly escape. Other fish can match the amount of sunlight above them and display it below them, making them nearly invisible to hunters who would attack from below. Finally, it is believed that fireflies primarily luminesce to attract mates.
Chemiluminescence reactions can also be seen in human practice. For example, the synthesized molecule luminol, which was mentioned at the beginning of this video, is used in crime scenes to check for blood. Crime scene investigators will start with a mixture of luminol and hydrogen peroxide, which they will then spray around the area. The iron in the blood catalyzes the oxidation of luminol by the hydrogen peroxide, emitting blue light. The picture on the left shows this in action. The investigators working at the scene have to act fast though, because the glow disappears quickly as the reaction goes to completion. The production of luminol follows the shown reaction scheme. First, hydrazine is heated with the 3-nitrophthalic acid. An acyl substitution condensation reaction occurs, forming 3-nitrothiohydrazide. The nitro group is then reduced to form luminol. This reaction can be performed in industry or in laboratories such as those here at Purdue. Pictured here is the mechanism for the chemiluminescence reaction with luminol, which we showed at the beginning of this video. This mechanism follows the same basic process as the one explained earlier for fireflies. Again, oxidation leads to an excited electronic state. To return to its ground state, the molecule then releases energy primarily in the form of light, leading to an observable glow. In this specific reaction, luminol reacts with the hydroxide ion, forming a dianion. The oxygen produced from the hydrogen peroxide then reacts with the luminol dianion. The product of this reaction, an unstable organic peroxide, is made by the loss of a nitrogen molecule, the change of electrons from excited state to ground state, and the emission of energy as a photon. This emission produces the blue glow that we can see. The following video is us performing a demonstration of a luminol reaction and the emission of cool blue light.
So in today's reaction, we'll be doing the reaction of luminol with our oxidizer, H2O2, and a catalyst. So the first thing we're going to do is we're going to take 1 scoop of our luminol mixture and add it to the solution. The next thing we're going to do is we're going to add our catalyst, copper sulfate. We're using copper sulfate today, but a variety of other metals, including magnesium and iron, will also work. Now that we have our luminol and our catalyst inside of the solution, all we need to do now is add the H2O2, and it should emit a blue light when it turns the lights off. So, observe. Add the H2O2, turn the lights off. And if you swirl it around a little bit, you'll see that a cool blue light is emitted. Now this is a cool light, which means it's not emitting any heat at all, it's just glowing blue. Now it looks like it disappeared on the screen, but you were able to see it there for a little bit. So that is today's reaction.
As our own demonstration produced a glow that was difficult to see on camera, we have provided another video of the luminol reaction that was performed here at Purdue University. In this lab, luminol was synthesized using the same reaction scheme previously discussed.
Oh my gosh.
Oh my gosh.
Wow.
This is
Definitely
the coolest
worth.
thing we've done all year.
This is the coolest thing.
Wow.
That's awesome. That is awesome.
I'd say it works, guys. Oh, sorry.
We did it right. Woo! Science.
Science.
Oh my
I
god.
think we could have seen that without the pinch it, man.
Yeah.
Where does it only work in the
There's a swirlies.
Swirl it?
Uh-huh.
Oh, that's cool.
So cool.
Humans use chemiluminescence in many other ways too. The example we are all most familiar with is glow sticks. Inside of a glow stick is 1 glass vial containing hydrogen peroxide, the oxidizer. When broken, it mixes with diphenyl oxalate, creating a glow that can last for hours. Other practical applications is in gene expression assays. Green fluorescent protein, which was originally discovered in a certain species of jellyfish, is often added to protein products. Researchers can determine if their protein binds correctly by measuring the luminescence given off by GFP, green fluorescent protein. Finally, nitric oxide reacts with ozone to form an electronically excited nitrogen dioxide molecule, which then luminesces. This reaction can be used to detect the presence of nitrogen monoxide in automobile exhaust or to test for high levels of ozone in an area. We've hoped you've enjoyed learning about chemiluminescence today in Real Life Orgo. Following are some bloopers for your viewing pleasure. So the first thing we're going to do is we're going to take our luminol and we're going to add it to our water mixture. Wow. See, H2O2 by itself is not actively not inactive. Under do you need to not be here? Maybe we should. Do you need to be the camera operator?